All right, let's talk about one of the absolute giants of calculus, integration. Yeah, I know, it has this reputation for being, well, a little scary, but we're going to change that right now. The goal here is simple, to give you a really clear mental map of what integration is, why it works the way it does, and how you can actually start using it. So, let's dive in.
So, before we get tangled up in any weird symbols or fancy rules, let's just start with a super simple idea. Imagine I tell you the answer to a problem is 10, and I got there by adding 3 to some number. What was the original number? Well, you'd just subtract 3, right? You'd work backward. You'd reverse the process. And believe it or not, that's basically what integration is. It's the undo button for another huge part of calculus.
Okay, here's our roadmap. First, we'll cover what integration even is. Then, we're going to decode all that notation. We'll solve the mystery of plus c, which I know gets a lot of people. Then we'll get into your basic toolkit, and finally, we'll touch on some more advanced techniques. Pretty straightforward, right? All right, section 1. What is integration? Let's get to the big idea here, because honestly, the main concept is way simpler than you might think. Okay, so if you've done any differentiation, you know it's all about finding a rate of change, right? Like if you have a function for a car's position, differentiation tells you its speed. Well, integration does the exact opposite. It's like if you have the speed, integration helps you rebuild the original position function. That's why we call the result an antiderivative. It's literally the thing you had before you took the derivative. It's the reverse. Moving on to section 2, decoding the notation. Okay, let's be real. This is where a lot of people's eyes glaze over. The symbols can look like some kind of secret language, but I promise you, it's not a code, it's more like a recipe, a set of instructions. And once you know what each ingredient does, the whole thing just clanks. First up, that big squiggly S-looking thing, that's the integral sign. And when you see it, it's just a signal. It's your cue to think, okay, go time, I need to find the antiderivative now. It's the command that kicks the whole process off. Okay, next is the fun of x, or whatever function is sitting right next to that integral sign. We call that the integrand. This is just the what of the problem. It's the function you're actually working on, the thing you need to reverse engineer. It's the piece you're trying to build back up. And then at the very end, you always see that little dx. That's the differential. Its job is super important, but really simple. It tells you which variable you care about. If you have a bunch of letters in your function, the dx says, hey, we're integrating with respect to x here. So yeah, think of the integral sign and the dx as a pair of bookends, and everything in between is what you're working on. So let's put it all together. The whole thing, integral f of x dx, is basically an instruction that says, find the antiderivative of this function, f of x, with respect to the variable x. And the answer is some new function, we'll call it big F of x, and then there's this little plus c tacked on at the end. And that little guy, that plus c, is probably one of the biggest headaches for people just starting out. So let's figure out what it's all about. All right, section 3, the mystery of plus c. Why is this thing in every single answer? What is the deal with the plus c? It might seem random, but the reason is actually really, really logical, and it all goes back to how derivatives work. Okay, Let's just run through a quick example. Check out the function x squared plus 1. What's its derivative? Well, the derivative of x squared is 2x, and the derivative of that constant 1 is just 0. So the derivative is 2x. Easy enough? Okay, now what about x squared plus, 63? Same deal. The derivative of x squared is 2x, and the derivative of 63 is 0. So we get the exact same answer, 2x. Let's do one more. The derivative of x squared plus 100? Yup, you already know. It's 2x again. Why? Because the derivative of any constant number is always 0. And this, right here, is the key to the whole mystery. So think about it. When we work backwards, when we try to integrate 2x, we know the answer has to have an x squared in it. But where did that 2x come from? Was it from x squared plus 1 or x squared plus 63? Or maybe just plain old x squared? The truth is, we have absolutely no way of knowing. That information about the constant was totally lost when the derivative was taken. So plus c is our way of saying that. It's a placeholder for any and all of those possible constants. It's not just one answer, it's a whole family of them. Okay, section 4. We've got the big ideas, we understand the language. Now it's time to actually get our hands dirty with your basic toolkit. These are the first rules you need to know, the ones that will let you solve a ton of problems right off the bat. Now, these first two rules are seriously powerful. First, the constant multiplier rule. This one's super easy. It just says if you have a constant number multiplied inside your integral, you can just pull it out front. It cleans things up. But the second one, the power rule, this is the absolute workhorse of basic integration. It's the perfect reverse of the power rule for derivatives. Remember how you'd bring the power down and subtract 1? Here, you do the opposite. You add 1 to the power, and then you divide by that new power. Seriously, these two rules are your bread and butter. You're going to use them all the time. Okay, final section. What happens when you run into problems that are a little tougher? The power rule won't work for everything, obviously. So for those, we need some more advanced techniques. Think of these as your pro moves for the really tricky problems. The two big ones you'll see are U-Substitution and integration by parts. And really, the whole game is just knowing which one to use. Here's a tip. If you look inside your integral and you see a function and its derivative kind of hanging out together, that is a massive clue to use U-Substitution. It's basically the reverse of the chain rule. On the other hand, if you just see two totally separate functions being multiplied, that's your signal to try integration by parts. That's the one that reverses the product rule. Now, integration by parts sounds scary, I get it, but it's really just a step-by-step process. The whole strategy is to take your hard integral and break it into two pieces, a u and a dv. Then you plug those pieces into a special formula. And the whole point of that formula is to trade your hard integral for a brand new one that's hopefully a lot easier to solve. It's just a recipe. You pick your u and dv, find du and v, plug them into the formula, and then you solve what's left. That's it. Okay, let's just quickly recap the whole mental map we've built here. Number 1. Integration is just differentiation in reverse. That's the main thing. 2, the notation isn't a secret code. It's a set of instructions. 3, you always need that plus c for indefinite integrals to account for the loss constant. 4, You can get so much done with just the basic rules, especially the power rule. And 5, for the really gnarly problems, there are advanced strategies like U-sub and integration by parts.
And that brings us right back to where we started, looking at this equation. But now, it's not just a bunch of weird symbols, is it? You know what it's asking for. You know what each piece of the answer means. And you've got the first tools in your belt to actually go and solve it. So it's not a scary monster anymore. It's a tool. The only question left is, what are you going to do with it?